stochastic processes based in physics in the 80s. He had been involved in many of the most important developments at that time. In particular, he was known for his work on the construction of fluctuations, ordinary motors, motion transitions, this concept of the Brownian refrigerator, in which you can cool a system just by making noise or shouting at it. And recently, he's been devoted towards what I find a very exciting new topic, because as I said 1 year ago, 1 year or 5 years ago, this is a new field in which, it's an old field in which new things are being said, which is the field of the second law of thermodynamics. What new insights have people like Chris been working on and developed what many facets of the second law, really the knowledge of what the second law really knows, really means, and really implies. He'll be with us 3 weeks this time. He'll be upstairs in the third floor.
Thank you very much. Thank you for the invitation, and it's a pleasure to be back. I don't know how loud I have to speak, because I'm being recorded, so I should be speaking loudly enough for everybody. Okay, so I'll speak loud. So yesterday what I did is I went to the internet and I looked at my own talk. It was very well. I mean, good quality. I was really surprised. So now I'm a bit scared because I realized it's out there. Anyway, so.
You were surprised by the talk.
So, but I was happily.
The recording or the talk?
I was happily surprised because I thought I already told you everything last year, but I didn't. And so actually, I think this is a very good opportunity, because last year I could feel that people were not completely convinced. That, I mean, I was telling about this revolution, about the interpretation of the second law, and I basically discussed the result. But I didn't tell how you could come to this result. And there are many roads. I mean, this is what happens when something new is discovered. It is discovered in many different ways, in many different shapes, but always the same thing comes out, and then you start to believe that this is a very basic, fundamental, and deep thing. And this is what I believe about these new developments. Now, what I will do today is I will show you one way to get these new results. It's not the only way, and it's of course very nice to check that you can get the same result using other physical inputs, but of course I have no time to do that. So the way, the road I will follow today is a road I think many of you know, and that's why it's a good choice. This is the road of stochastic processes. So I will show you how you can develop thermodynamics and new concepts in thermodynamics based on a stochastic description. And I will show that for a discrete stochastic description, namely the mass equation. Now, I will sometimes, maybe I will not show you all the proofs, but I'm here, and on the slides I have the proofs, and I have also proceedings of a Varanian summer school, where actually this talk that I give today is really written out in full detail. And so you can, of course, ask me for these proceedings, and of course you can ask me if you want some more details, and I'm also prepared, if there is interest, to have some special sessions to go through the calculations and to show you how everything is done. It's not very difficult with these stochastic processes, so that's very nice. So, okay, let me just briefly, in a nutshell, tell you what is thermodynamics, or how I will. So, I will derive a formalism that is formally identical to standard thermodynamics, but there will be, of course, new elements in it. So, let me recall the first law of thermodynamics is, of course, conservation of energy. So that means that the change of energy is only due to an input of energy, an exchange of energy with an external agent. And so this is a way to write the first and second law in the same way. So this is the creation of energy zero. This is what we mean by this formula here. So there is no internal creation of energy. The energy change of the system is only due to exchange with the outside world. And this exchange can have many different forms, but there are 3 forms that are of interest to us. There is work, so there can be a force acting on the system, for instance, a pressure, and this generates work, which will, of course, change the energy of the system. You can exchange particles, there will be chemical energy, and this has, I mean, a typical example of this is, of course, the minus VdV, which you know from standard thermodynamics. the chemical exchange of particles gives rise to an energy change, which is the chemical potential times the number of particles that is exchanged, and the heat that is exchanged with the system gives rise to TdS form. This is the form that you have in standard thermodynamics when the exchanges are quasi-static, so that you have equilibrium actually all along. This is the first law. The second law, write it on the same way. So there is E is here the state function for the first law. The entropy is, of course, the state function for the second law. So it's something that only depends on the state of a system. And it changes now due to two contributions. One is an exchange term, which is because when you exchange heat with a reservoir that has a temperature T, then the entropy changes by this amount. And the other is a positive contribution which takes place inside the system. It's an irreversible process. The only thing that the second law says about this is that this has to be positive. Okay? There is another formulation of this which actually combines these two laws for a system in contact with a heat bath. I mean, this is the system, this is the heat bath. You see, if you combine the first and the second law, you can actually, so you look at this term multiplied by t. This term here you know because it's given by that. And then you use the first law to replace the dq. And if you do the calculation, it turns out that if you introduce this function here as the free energy, which you may recognize, E minus ds, you see that the second law can be rewritten as a limit on the work that you get out of a system or perform on a system in terms of its free energy change. These are three basic formulations of thermodynamics that you can find in standard. Now, don't be afraid. I mean, if you don't even remember this, it's okay. It's okay. Because I just will derive this. I will derive formulas that are exactly the same as these ones, but I will derive them. Then I will show you that you can go beyond these formulas. Maybe I can already tell you a little bit what we will do. One of the things is that we will be able to identify what this thing is. So we will have an expression for this thing, DIS. Normal thermodynamics tells you, okay, there is an irreversible process, but this is outside the scope of normal thermodynamics because this irreversible process is due to the fact the system is out of equilibrium, and thermodynamics doesn't tell you what's happening when something is out of equilibrium, except that this entropy production has to be done. So we'll be able to identify this thing. So this means that we are actually doing, this is the first major advance, we will be able to do thermodynamics but out of equilibrium, and we will be able to identify this positive quantity explicitly. This is already very nice and okay, and I will show you some applications of that, but the major advance is that we will also be formulating thermodynamics trajectory-wise. This will become clear at the moment that I introduce this stochastic. So now, just to remind you also, what is it that we will use? We will use a system described by discrete states, which I will represent by the index m. And the state of the system is not necessarily where it is, but there is a probability distribution. So what you know about the system is that it has a certain probability, Pm, to be in state m. That's the first thing. This describes what I call the state of the system, is the probabilities. The second thing is that I have for this system a law of evolution of its state, of its probability distribution, and I assume that this law of evolution is Markovian. So I have something of the following type. The probability to be in state m at time t plus dt is a probability to be in another state at time t and to make a transition, and then I have, of course, to specify a transition rate that describes the system, which I have here identified with this W. And then I have, of course, the probability that I'm in state M, I don't make transitions. Okay? And if you write this under differential form, you get the familiar equation called the master equation, which tells you what is the law of evolution of this problem. Okay? And so here we have the transition matrix. It has the following properties. The off-diagonal elements, these are the rates of transition. These are positive quantities. This is a probability per unit time. It's a probability per unit time to make a jump. So it has to be positive. And here the trick, this is just a notation, but it's very convenient. we kind of put all this sum here, this minus the sum over these guys, we call it the probability to remain in the state. Okay, so this is W, this is diagonal element, this is this minus this sum, and this is obviously negative, because these are all positive quantities. So that's all we need to know. Okay, we'll have to do a little bit more to connect with physics, because this is just a stochastic model, and I have not introduced physics at all. But this will be the starting point to build our thermodynamics. Okay? So as I said, I will first reproduce more or less standard thermodynamics, except that I can go as far out of equilibrium as I want. But I call it standard in the sense that I'm working at the ensemble level. I will work with averages. Okay? And then I'll have a second section where I will work trajectory-wise, where I will follow not the average of the system, but I will follow the actual system. Okay? But let's first start with the ensemble picture, and I want to reproduce the first law. So remember, what is the ingredient? I have such an equation, and the state of the system is described by this probability distribution. Of course, to introduce the first law, I have to introduce the concept of energy. Okay? And so this I do by saying that every state M, it's a kind of microstate, I attribute to it a certain energy. Okay? So there I'm starting to do physics. So state M has energy epsilon M. I will suppose it's non-degenerate for simplicity. And then also every state could correspond to a certain number of particles in the system. So if M changes, it means the energy changed, but also the number of particles can change. So it means that there is, of course, an energy flux and a particle flux and such and such. Okay, what I call the energy? It's just this average. So this is the state of the system. Probably to be state M is PM. This is the energy state M. This is, of course, the average energy. And this is the number of particles, average number of particles. This I call ensemble picture, because I describe the average properties of such a system. Now, how do you get the first law? Well, how can this E change? Well, you see, there are two factors. It can change because this guy changes or because this guy changes. So this I've written here. The change in E is some epsilon M, the change in P, or there is another contribution, P times the change in E. So there are two contributions to the energy change, and we can identify them. I will show you why this is so. This term here, this change, is work. Why? This is what you will find in the normal books of statistics. I'm doing what is written in the book of statistical mechanics. So if you have an energy level that is occupied and you move it, well, this work comes because you apply a field, for instance. You're changing the energy levels. How can you change the energy levels of the system? You can, for instance, change its volume by applying a pressure. Then the energy levels change. Or you can change the energy level if you have a charged particle by changing the electric field. So this contribution here is the work. And then this contribution has to be, because you remember what we had before, so this is the work contribution, for example, this type of thing. Here we have a sum of two contributions. One is heat and one is chemical work. Okay? So now, to make this a little bit more concrete, I have to say something more about this transition probability. So the first thing is, because that will be of interest, the transition probabilities are due to the contact of your system with one reservoir or more than one reservoir. It's interesting actually to have contact with more than one reservoir, because then you can, of course, generate non-equilibrium steady state, for example. So what we assume is that the transition rate is a sum of transition rates due to contact with different reservoirs. So there is in general a sum over nu are the reservoirs that I'm looking at. Then the other thing is, what about these guys themselves, these transition rates? Well, the idea is the following. Suppose that I have my system in contact with only one reservoir. So I switch off all the other rates. And I wait. What happens? The system has to go to equilibrium. Okay? It will go to a distribution. But this distribution, in order to have a physical system, it has to correspond to what statistical physics prescribes. And what does statistical physics describe? That a system in contact with a reservoir with a certain chemical potential and certain temperature, when it relaxes, it goes through the grand canonical distribution, which is written here. So the probability for this system, when it's in contact with reservoir nu, the probability to be in state M is exponential of minus 1 over the temperature of the reservoir, the energy of the system. This is the normal Boltzmann factor. This is when you have also particle exchange. This is the grand canonical distribution, and this is normalization factor. This is what statistical physics, what physics prescribes. And so there is an additional property. We know that in equilibrium you also have detailed balance. So it's not enough to reproduce this distribution, but you need to have that the probability at equilibrium to go from m prime to m, which is given by this term, is equal to the probability to go from m to m prime. So these are conditions which are imposed by what we know from physics. Okay, so this condition will be the balance. This gives you a condition on the transition rates, and we will assume that this condition is verified. Now, the second thing is I was telling you that the change of energy corresponds to work. So if I have a system sitting in some energy level and I move the energy level, I will call this work. Okay. Of course, to have if I'm changing the energy levels by some, this is the idea, there is an external work source, an electric field or whatever. Of course, I'm also, because I require this to be valid at all times, I'm actually making, you see, if this becomes time dependent, I will actually need to make the transition rates to be consistent with this condition time dependent. Okay, so what is the whole setup? So the setup is we have a stochastic process described by a mass equation. The transition rates satisfy this property. This is the sum over transition rates of different reservoirs. With each reservoir I have this property. And then eventually, if this epsilon here is time dependent, then the rates adapt. They have to adapt to always satisfy this condition. But this time dependent can give rise to work. Okay. Now, one property that we will use, I will mention it soon, is that if you have this condition here, and you take the logarithm of the rate to go from m prime to m and the rate to go from m to m prime, well, this actually has a very nice meaning. It's 1 over the temperature, okay, Kb is always there, times the elementary heat that is exchanged with the reservoir when I go from m to m prime. Why? Because if you just fill this out, so you take the ratio of these guys, is the ratio of the probability distributions, ratio of the probability distributions, to take the logarithm, you have the beta that comes out. This is a normalization constant that disappears. And you see that according to with these rates, this is indeed what I wrote before on my previous slides. This is the heat that the system exchanges. So it's change of energy minus the chemical contribution. This is the heat that the system exchanges with energy.
Why do you associate the chemical energy only to the change in probability and not to cannot?
Because, okay, this is the change. Okay, I forgot to say this. So when an energy level moves, the assumption is that the number of particles in a certain energy level does not change. The only way to change the particle numbers is if you jump from one level to another. Okay, so
this is assuming that there are independent particles.
No, I mean the state of the system is described by an index m. For a given index m, I have a specific number of particles. This I assume. So I can only change the number of particles by jumping from m to another level, from one level to another level. This could be, the levels could be the number of particles, by the way. So you just have to do it in that way. Okay? Okay, so this is the first law. Now what about the second law? Okay, so again, this is my equation, and now I have added here this, I have split this into sum over the different reservoirs. So I have, of course, now to introduce an entropy. And the entropy I write down is this one. So I have a probability distribution. This is the Shannon entropy. I multiply by Kb. Well, why is this good? Well, first observation. If this is the equilibrium distribution that I showed you before, then this is indeed thermodynamic entropy. So at equilibrium, it produces the correct thermodynamic entropy. Also, you can check if you make a quasi-static change, this object reproduces the basic law, the standard law of equilibrium thermodynamics. So within this context, I just reproduce what thermodynamics prescribes. So at equilibrium, it's okay, or close to equilibrium, it's okay. But let me see what is the change. I mean, because I have an evolution law for this guy, I can write evolution law for this guy. Okay, so I do it, and this is, I will not go, I mean, this is what I mean. I can show you in detail, or you can look at yourself, but it's not long. You can see it's not long. You just take the derivative of this guy. This is the derivative of this sine logarithm. The other derivative on this guy goes out because of normalization. Here you replace it by this law. Then you make a small trick here. You write this. These are dummy indices. You do them double and you divide by 2. And then here you multiply and divide by this extra term. So what you get? What you get is that the entropy change is a sum of 2 contributions. Okay, this S dot is a sum of 2 contributions, one of which you immediately see that it is always positive. I constructed it in that way. You see, it's this minus this times the logarithm of the first guy over the second guy. It's x minus y log of x over y. So this is always positive. Okay, so this is this thing here. This is of course always positive. And it's only positive, it's only 0 if x is equal to y. Okay? So that is of course extremely nice. I stress this term, it's only 0 when every single term in that sum is 0. Every single term in, this is a 3 doubles, I mean it's a term of m prime u, but all these terms are separately positive. Okay? So this object is only 0 when all these terms are 0. And this is what I will show you. This is exactly what we expect for equilibrium with no entropy production. Because the idea is, of course, this is entropy produced inside the system. It can only be 0 if there is detailed balance, if every process obeys detailed balance inside the system. And then, of course, the check will be, is this indeed what thermodynamics prescribes? Is this the entropy change? It should be related to the heat. In the way that we did before. Okay, so let's check. Okay, so by the way, so yeah, this is of course a real derivative. This is separation. I use this notation. It's not there is no such thing as I in itself, but this I can find S dot I and S dot E. So these are 2 contributions. Okay. Now it's interesting to rewrite to show that this has really the what you expect for an entropy production. It's interesting to introduce this quantity here. This quantity. Actually, I wrote it here. What is it? This quantity, well, this is the net flux of transitions from m prime to n. So I have this, the state of the system is P, and I ask at that moment, how many net transitions are there from m prime to n net? So I count the ones from m prime to n positive and the other ones negative. So this is on average number of transitions in one direction. This is the average number of transitions in the other direction. So this is the net average number of transitions. This is the flux in this. So you have 2 levels, and between them, either there is on average nothing, so as many ups and as downs, or there is a flux in one direction or the other.
Why average? Because you consider both directions?
No, because I do the average with P.
Ah, right,
it's
okay.
with the probability distribution. So I have the probability distribution tells me if I am in one state, of course, I can only jump out of the state. But I have a probability distribution, and so I can calculate on average, given this probability, how often will you see transition in one way, and how often will you see transition in the other. This here, it's a logarithm of these 2. It basically tells you, because this is detailed balance means there are as many transitions up as down, so this is 0. And it's the same here. This is a kind of force. This is the deriving force. It tells you how strongly in these transitions between m prime and m, you deviate from detailed balance. When you have detailed balance, this is equal to that. The logarithm of 1 is 0. With this structure, this is very nice because you see you can now rewrite this first positive thing. It's like also this is like in linear irreversible thermodynamics, but anyways, that's what shows up here. The entropy production is a sum of fluxes times forces. This is the net flux of transitions between these 2 states, and this is the force between the transitions. I mean, I've written them in that way. And as I mentioned before, every single term here is positive.
M prime or M?
Yeah, I see there is an error. C. I'm sorry, this has to be m prime, x m prime. Okay. But what really confirms that we are on a good track is if we look at this quantity now. Okay. So now I remind you that because of detailed balance on these rates, the logarithm of this ratio was, as I wrote before this formula, was the heat that is exchanged when you go make a transition from M to M prime. And so I just write out the formula. So this is this elementary heat times the number of such transitions, net transitions. This gives you the real heat flow from reservoir nu divided by the temperature of reservoir nu. And you find here the expression that thermodynamics prescribes. Big difference, so I have now an explicit expression for this quantity. It is positive, but I know exactly what it is. Okay. So, now I will show you 3 applications, but I will go fast. Just to convince you that it's not just, formulas and you cannot do anything with it. I will go a little bit faster because I want, of course, to go to the even more interesting aspect is trajectory thermodynamics. So let me show you what you can do. So, of course, if you have a stochastic description, then you can apply this formalism. Okay, and so this is what is the model that I have here. I have a quantum dot, so it's a space here where one electron can sit, or no electrons. So there are 2 states. So there is an electron, there is no electron, and I put it in contact with my 2 reservoirs, which are fermionic electron reservoirs, but I put them at different temperatures and different chemical potentials. So you know, this is the Fermi level. All the electrons normally fill up to there, but at the final temperature, you have this profile here, broadening around the Fermi level, and the same one here. And the idea is, of course, that these 2 temperatures need not be the same, these 2 chemical potentials need not be the same. Now, this guy here in the middle is filling both reservoirs. It can exchange electrons with both reservoirs. So it is in a non-equilibrium state, and it can be far from equilibrium, because these temperatures and chemical potentials can be anything. Okay? So what is the description? Well, the electrons, of course, jump in and out on both sides. And I just use what you will find in the standard textbook. The simplest approximation for that is that the rate, well, it has a very simple meaning. An electron that is sitting here can jump out if this level is empty. And occupation probability for the level is the fermionic distribution. So the probability of not being occupied is 1 minus the fermionic distribution. This is this. There is a prefactor which tells you kind of how close contact there is between this dot and the lead. And the same on the other side. Okay? And the other way, an electron can jump into an empty quantum dot, of course, if there is an electron, and the probability for having an electron is the fermionic distribution. So I have this thing. Okay? So I put it in here, and then I can, I have a stochastic process. I can calculate everything. I just show you the result. For instance, the entropy production that you find for this model is given by this. Okay? Just give you the result. These are x's, so you introduce these quantities, which are basically tell you the deviation between this energy level, the chemical potential, with respect to the temperature that is observed in that reservoir. So it's a kind of relative distance, and the relative distance there. And it turns out that entropy, of course, it's always a positive function. You can immediately check. It has to be that. But one amusing observation is that the entropy production is 0 when x1 is equal to x2. And x1 equal to x2 means not that both temperatures and both chemical potentials need to be equal. It's only one constraint. So what it actually, but you can, a physicist would have seen that. So of course I'm not finding something that is unphysical. But basically the condition is there is no entropy production if this energy level is chosen such that occupation probability here and there are the same. You see? So you could have that here you have a very high potential, but a low temperature, so actually it drops off quite quickly. Here you can have a lower level, but a high temperature, so it drops off more slowly. So actually the occupation probability here and there could be the same, and this is precisely this condition. In this condition, you have one level which is in contact with 2 reservoirs at different temperature and different chemical potential, and still you have equilibrium. There will be no flow. Of course, this is an approximation that there is no broadening of, you can have more complicated modes, but in this simple mode, this is what happens. So this is an example of a non-equilibrium steady state. Another thing you can, we studied actually is the case when there is a driving. So suppose this is a very high temperature, and this is a low temperature, well, I can drive particles from the high temperature to the low temperature. I can drive them up in chemical potential. So then I have a thermal engine. I use the temperature gradient to pump particles up. And one of the things we looked at is the efficiency of such a machine far away from equilibrium. At equilibrium, calculation will immediately give you, it's 2 lines, I will find Carnot efficiency. But I can also, because I have a formalism valid out of equilibrium, I can, for instance, calculate the efficiency at maximum power. Okay, what else can you do? Well, in the same problem, you can ask the question, suppose that I have a quantum dot and I'm going to move it up in energy level by, for instance, turning on an electric field. Well, of course, if there is an electron in there and I move it up, I will perform work. But of course, if I move it up, probably the electron will jump out because you move, when you start here, for instance, this is far below the Fermi level, it is occupied, and if I move up there, it will have jumped. Okay? Where it has jumped, well, it depends. It's a stochastic world, so it will, it can of course jump back in, and even that's all possible. So, but one of the questions we studied is, what is the scenario for which the work that is needed to move this level up from beginning to final point is minimal? Okay. Well, this is again this master equation, and what is amusing is, of course, the rate of jumping has to do with the, it's time dependent now because my energy level is going up, but you have, this is here the Fermi factor for those who recognize. You have actually a relation between the position of the energy level, the probability, and via the mass equation with T and P dot. Okay? And now I come back to what I said before. The work is the change of energy, and here I have done it continuous time. So this is the work. The energy change I can also write. This is the heat. And what I can do is I want to minimize this, which actually corresponds to maximize this. But epsilon I can solve from there. If I do that, I get actually for the heat, which I want to minimize, I get an Euler-Lagrange problem. You see? In terms of this P, okay? This is the Euler-Lagrange, and you can solve the Euler-Lagrange equation, almost. Apart from there is something. And so you can actually, for instance, in this case, I ask, what is the optimal path to move the level up from below to above the Fermi level? And this is, for instance, the optimal path. It has a jump. It's discontinuous. It has a jump. Then it's a continuous branch, and then again it's a continuous branch. So this is out of equilibrium with driving. But I do the whole thermodynamic analysis, and in this case for the work or the heat, I could of course also look at entropy. And actually, what we did is we actually did a whole analysis where we use such a system to make, again, the same machine that I mentioned. So you have different reservoirs at different temperature. But now I make a thermal engine a la Carnot. And if you remember, Carnot, it's only in contact always with one reservoir. So you're in one reservoir, you do something, you disconnect, you do something, you go to another reservoir, you do something, you disconnect, you do something. So you make a whole Carnot engine from this, and you can, for instance, again check that you have Carnot efficiency if you work reversibly and all that. So then very briefly, just to tell you this thing about non-equilibrium. So you can basically write all the formulas as before, with this difference that the concepts are defined out of equilibrium. So the entropy I had before is defined out of equilibrium, so I can also define free energy out of equilibrium. And then it's interesting to compare this free energy with the free energy that you would have when you are at equilibrium. What can you show? It's again a one-line calculation. You can show that the free energy of a system, when the system is not at equilibrium, it has a higher free energy. So whenever your system is not in equilibrium, you can extract more work. Okay? But you have the explicit expression for that. Okay, so it has an explicit expression. Okay. And what is a way to prepare? Well, there is one very intriguing way of preparing a system out of equilibrium, is to measure it. I have a system at equilibrium, but I look at it. And then I know more or less where it is. So that means that the original probability distribution, which is, of course, this grand canonical, for instance, becomes something else when I look at it. And then I can extract work. So this has to do with the whole discussion of thermodynamics of information. Of course, the reason why you can do that is because when you look at it, you have to use an information device to do that. So this is the discussion with Zille. But for instance, here I just give this example here. If you have a gas and you look at it and you know that the gas is in this side, well, this is here the expression for this difference in free energy. It's a very simple case. What you basically have, the equilibrium distribution is distributed uniformly over the whole cell. When I know it's here, my distribution that I now have is twice the equilibrium distribution here and 0 there. And so this is actually the expression of this difference, and you just fill it out, and you will find that this is KT log 2, which is extra work you can of course extract when you know that the system is on one side. You insert a piston, and then you can let it expand. There is more, but I have no time. So now, trajectory thermodynamics. So this is already very nice that we can go out of equilibrium and do standard thermodynamics. This is not really the big message I want, the real spectacular, revolutionary advance that I want to mention. To introduce this other aspect, actually I think I already mentioned this last year, but I want to go back to what I wrote before. This is one version of the second law, and I want maybe just to tell you again in detail what it is. I have a system in contact with a heat bath, and I change its state from A to B. Equilibrium state A, I do something, equilibrium state B. In between, I have to perform or I receive work. Okay? What does the second law tell you? It doesn't tell you exactly how much work you get. It gives you a bound. Okay? What does it tell? Well, the total entropy of this whole device cannot increase. That's the second law. And if you do the calculation, you will find that in this particular case, this change is the work minus the difference of free energy. So you have a free energy of the system in this state and a free energy of the system in this state. So if one free energy is different from the other, then this is the work performed on the system. Okay? You see that this work performed on the system is bound by the difference in free energy. If the difference of free energy is negative, your work could be negative, which means you extract work. But it doesn't have to be. If you're stupid, even though you lose free energy, you still perform work. That's what the second law tells you. Okay? It just tells you the most you can get out is if you have a decrease of free energy, you can get out work. That's when you work together. But look now, if I do this experiment with a small scale system, there is a slight problem, because and people have done this experiment, they take a bead and they move it from one position to another. Well, this is a very fluctuating environment, and it could well be that in this experiment you get work instead of performing work. The sign of the work changes all the time. So actually this experiment is not described by something, the W is described by a probability distribution. Now what does traditional thermodynamics tell you about this? They say, well, this is of course a small scale system, thermodynamics does not apply. But if I put a lot of these strands parallel until I have a macroscopic number of them, then the fluctuations will average out, and then the second law will apply. So the second law will apply to the average of this quantity. Now this I have always found very strange. How could a fundamental law of physics just tell you something about a moment of a probability distribution? This is weird, no? I mean, this very basic law just tell, okay, I don't know what probability distribution is, I don't know. I only know that on average you have to do more work than this difference in free energy. Okay? And okay, this is not an academic question. Of course, before it was an academic question, but of course now people can really monitor such small-scale systems. I mean, biologically, for instance, biologically, this guy here, there is a gradient in chemical potential in, for instance, hydrogen, that drives this engine. And normally, so of course, the gradient is such that you would only have rotations in one direction. But because it's a small engine, there are thermal fluctuations also in what this guy does. And so you see that in the trace that sometimes the motor turns against what is expected from the second law on average. The same here with single electron transistors. Electron may jump up in potential instead of jump down. so it can be measured. Okay. So what I will do now is I'm going to reformulate the first and the second law of thermodynamics for trajectories. So the state of the system is no longer the probability distribution. It is there is a probability distribution. But when I see the system, it is in an actual state. And I want to reformulate both first and second law for a specific trajectory of my system. So for the energy, it's actually quite easy. So here I have plotted what could happen. So this is time. This is the energy. Okay, suppose the system starts, I see it. So it's from an ensemble, of course. Initially, there is a distribution, but I observe the system. And it is in state M1 up to this time. And as I mentioned, the energies can be time dependent because I can do work on them. Then I have a jump. This is, of course, I have exchanged heat. So this energy comes from the heat reservoir. Then I'm in M2, then I'm jump again, and so on, and so on, and so on. And I enter there. This is what I wrote before. The energy of the system is this statistical average. What is the analog trajectory? Of course, well, the energy is just the energy it has. So I've used this notation. Energy at time t is the energy level in which it is with the energy it has at that time. So the energy levels move. And of course, also the system can jump from one level to another. So I have these two time dependencies. What is the change of energy that was... So here I have let's suppose no exchange of particles. So you can include it, but let's forget about it for now. So I have two contributions. I have heat and work. And you remember, of course, it has to do, the heat is the change in P and the work is a change in E. Here I can do exactly the same. I mean, you can see it very easily, of course, on the graph. The difference of energy between this level and this level is, of course, that here I have a difference. Here I have difference of energy. These are work parts, and then these jumps are heat parts. So I go from this energy level to this energy by summing all of these things. So these are all work parts that also move up and down, and then have a jump part. So I immediately have also that the change in energy is a small q plus a small v. So I use small notations for all the trajectories. So this is not a big deal. I mean, now the second law. So I have again the same trajectory, and remember I forgot here the constant KB1. Entropy was this. And this, of course, you see, of course, it's an average of something, like the energy was an average of something. I mean, it's a funny average because it's an ensemble average. It's an average with the logarithm of P. Well, what is the trajectory thing? Well, you have to remember, I am still looking at the stochastic system whose dynamics is described by a probability distribution. And so if I rerun the system, I will find something else. And the probabilities are described by this master equation. So at every moment, I can still define, I still have a well-defined probability. If the system happens to be in state M of t, well, there is a certain probability for that in this experiment. I have an equation for that. So I define the trajectory entropy. So at each moment here, this is well-defined. So each moment this is well-defined. I am here, well, I call the entropy minus the log of the probability of the state in which I happen to be at time t. This is for this guy. I can define at every moment for this entropy. Then I had these laws before. I mean, the change of entropy had two contributions, an exchange and an irreversible term. The exchange rate was the heat that comes from reservoir nu over the temperature of reservoir nu, sum over all nu. Well, I want to see if I can do the same, okay? So I write, of course, the small s's here. And now what is nice is this is easy to guess how it will work. So, of course, this was the average heat exchanged with the reservoir, and this average heat, it has to do with the sum of all these contributions, of course, but I can also define them in the trajectory. I know, okay, at this moment here, I should have specified, this is like for one reservoir, I know this jump is due to reservoir nu, so I could even put a subindex here. This is another reservoir. So I can, of course, see how much heat has it exchanged with reservoir nu, divided by the temperature, and I sum over all the reservoirs, and this I call DES. I know this because I know this. I know this because I know this. So I can find out what is this quantity. This is, of course, an intriguing quantity. This is the analog of my entropy production. Okay, now I write immediately the result. This is the result that I wrote down last year. Okay, and which we have to believe. Still here, I can show you. I mean, it's not very long to derive it, and I will not do it in detail still. But this is what comes out. If I put in this definition of the entropy, this is the entropy exchange, and I find this guy is this local entropy, this is the entropy production for a trajectory. Okay? I have to tell you what these guys are. So, okay, let me show you. So, well, here is actually the proof. So, you see, it's not very long. Eh? So I have, this guy is what I'm searching for. It's, oh, this has to be the other way around, I think. It's minus ds plus ds. Anyways. Why is this? Okay, well, I don't know. This guy I know, this guy I know. I write them down here. And now, what is the point? The point is that this quantity is the logarithm of what? It's the logarithm of the probability of observing this particular trajectory that I'm looking at. So this is the entropy change for this particular trajectory. When this particular trajectory has a certain probability of occurring. Okay? Which I call P of pi. Pi is the notation for a trajectory. And what I need now is another probability. I introduce a probability for seeing this trajectory if I would run the experiment backward in time. So I would, what does it mean? So what is the time dependence? The time dependence is I'm moving these energy levels, okay? Well, I'm going to move them in the time reversed fashion. This is exactly what I do. So here the energy level went up. The reverse experiment is basically retracing. So here I'm going down, okay? And then I ask, what is the probability in this reverse experiment of seeing the same reverse trajectory? So this is, I do tilde for reversing. And so I have the reverse trajectory in the reverse experiment. But if you calculate the logarithm of this ratio here, you will find exactly this quantity here. And it has to do with the fact that the, okay, so let's skip the proof, but it's not very difficult. I mean, I've explained it here a little bit. Okay, now, why is this a very pleasing result? Well, the first thing you can do is, with this result, I mean, this is what was the macroscopic expression that I had before. For in contact with a single heat reservoir, the entropy production is work minus free energy. Well, this you can literally rewrite this with the small s's. So this connection here remains the same with the small notations. So you still have a relation between the work and the stochastic entropy production and difference in free energy if you work trajectory. So that's already nice, okay? But one important thing is, of course, what about the sign of this guy? Well, it doesn't have a definite sign. So this is maybe, well, this we are happy, but this guy doesn't have a definite sign, but what about the average? Well, how do you find the average? Well, this is the probability to observe this trajectory. So this is for this, so of course if I have to average with a probability to observe a trajectory. This is what I do, and I have to sum over all the trajectories. Well, this quantity, first, I have a separate slide about this. This quantity is in agreement with what I had before. You remember I wrote on the ensemble level, I gave you the formula for the entropy production. You remember I showed you that the entropy production at the ensemble level can be split into two terms. One of these terms was that. Well, this is actually the differential form of this. You can prove. It's also a little bit, okay, you have to sit down and look at it. So this is consistent. So this guy, on average, reproduces what I had before. On average, it is positive. So that all looks very good. Okay. So now, let me again a little bit look at the implications, if this is true. Okay. So I have this entropy production, which was related to the work and free energy difference in this way, is the logarithm of the ratio of two probabilities. Probability of seeing the forward trajectory in this experiment and probability of seeing the backward trajectory in the backward experiment. This is well defined. But then there is, so okay, the average I mentioned is what I had before, so it has to be positive, but you can immediately see that this is positive because this thing here, this is called the Kullback-Leibler distance. This is the distance between this probability, kind of distance between this probability distribution and this probability distribution. And it is only zero when these two probability distributions are exactly identical. So what does it mean? I have a probability of seeing trajectories in the forward experiment. I have probabilities of seeing backward trajectories in the backward experiment. If these two probabilities are the same for all trajectories, I'm at equilibrium. But this means you cannot decide about the direction of time even by looking at trajectories. This is what equilibrium really is. every trajectory and its reverse are equally probable at equilibrium. This is what this formula tells you. The entropy production, this average, is the error of time. Whenever at some point there is a difference between the movie running forward and backward, then you have entropy production. You are out of it. But what are now the more recent results that, if this is true, of course you would like to find some implications that are not trivial. This is known, of course. Well, one of the things you do is you take this guy, you take a minus sign, you take the exponential of it, and you average it. Okay, and this was given by this. Well, what is it? So if I take minus sign and exponent, I basically put the p tilde on top and the p below with the minus sign, and the exponent kills the logarithm. So I'm calculating this average. But this average is, of course, the average with respect to this p, the probability distribution. This cancels out, and this is also a probability distribution, so it's normalized, so it's 1. So if this result is true, this quantity should be equal to 1 always. It's an equality. This is an inequality, this is an equality. So already we have, instead of saying that the second law is an inequality, I say, well, this guy is a second law in a better version of a second law. This is an equality, and actually this implies this. You cannot satisfy this equality except if the average is positive. So it includes this result. This is called integral fluctuation theorem, or sometimes work theorem if you apply it in the version with the work. Now it's interesting to rewrite this average as follows. So this is the average, but I can say, okay, what is the average? It's the average over this quantity. So I do, sorry about this arrow here. This is integral over all the possible values of this guy times the probability of this guy times this thing here. I don't know what happens to the arrow. But you see, I've just write out this thing, this average. And this is 1. Okay, this is what this says. But look, this means, if this is true, this means that this quantity here is a probability distribution. Why? Because this quantity is positive. This is positive, this is positive. And it's normalized. So if this integral fluctuation theorem is valid, there is a quantity, another quantity, which I call p tilde, such that the ratio of these two guys is exponential of delta ES. This I just write the fact that these two are equal, I rewrite it, and I get this. This is called the detailed fluctuation theorem. Okay? And in fact, okay, it requires a little bit more. I mean, this is because I can immediately write it here, but this p tilde, under certain conditions, is really the probability distribution in the reverse experiment. Okay? So that's why I use the same notation tilde as I had before. Now, one detail I just mentioned, I cannot say this at this point, but this free energy is a trajectory free energy. Well, it turns out that if you go from an equilibrium state to an equilibrium state, this free energy is equal to the equilibrium free energy and doesn't depend anymore on the state. This is a kind of funny thing, but this is what it is. So it means that if you have a transition between equilibrium states, this guy is really the traditional free energy, and this is what is known in the literature as the Crookes relation. And then this is known in the literature as the Jarzynski relation. They were originally, well, the Jarzynski relation, for instance, was originally derived in Hamiltonian context, not at all with stochastic process, just Hamiltonian derivation. And they work from equilibrium to equilibrium. We see we can go from any state to any state, but then this quantity also appears. If we go from equilibrium to equilibrium, then this quantity becomes equilibrium, free energy, and you have a simple result. Okay, so there are a lot of papers about this. And I think I showed last year, I don't remember, I showed 3 illustrations of this result. So, these original experiments of RNA opening have actually been performed, and this relation has been verified. So this is one of the very beautiful first experiments. So they measure this stochastic work, and they find that it obeys this relation that I mentioned here. We did a computer experiment, you see. In order to find fluctuations, of course, to measure probability distribution, it's better to work with small systems. But this is why computers are exactly fit for that. You make small systems, and these are, for instance, are disk simulations with a triangle that you move in a gas, so the gas is a hard disk, and you ask how much work does it cost to move from there to there, and you can do 500,000 runs, and you have a probability distribution. You do it in faster speed, slower speed, and so on, but this relation always has to hold, and it always holds. And this was a thought experiment that I mentioned because the derivations exist for Markov system, non-Markov system, for some quantum, Hamiltonian. Some people have written some paper about relativistic things. But this is, for instance, a thought experiment where you can show that in order to find the correct fluctuation theorem, you actually have to use the photon count that comes from quantum field theory. So I think this is typical for things that are very deep, like the second law, and I think this too. When you apply them outside the scope of where they have been derived for, you see that they pass the consistency test. So if you use the photon counts that Glauber derived, you can see that this entropy production indeed obeys the fluctuation test. So there is more, and at the time you can fall asleep. Okay? But if you want, I can send you the copy of my proceedings. Unfortunately, it has not yet appeared, but I have the proofs of it, in which I explain this all and a lot more in really detail. So you can follow the calculations, but I will always be ready to help you. And so, I mean, this is basically it's a summary. So this is the basic formula, if you want to remember, that the second law is replaced by an expression for the entropy production for a trajectory. And it has this very specific form. It's a logarithm of the ratio of two probabilities. And because of that, you have this integral and detailed fluctuation terms. And we hope to apply this, of course, in small-scale systems, especially in small-scale systems. There are still open issues in the quantum forum. And actually, for left here, one of the things that we have started is a cost action where we will see if our concepts can, for instance, be used to say something about quantum code. Thank you very much for that.
Okay, thank you for the talk. Any questions?
This kind of formulas are derived from many inputs. You have mentioned from Hamiltonian dynamics, from Markov process. Of course, this cannot be derived from anything. Probably some non-standard, non-Markovian process will be violate them, I guess.
I don't think so.
So my question is, yes. What is the minimum? What is the physical input required to this?
So okay, I will ask you. I will immediately ask first your. So one of the things we did, of course, it's if you can derive some of these things from Hamiltonian dynamics. So suppose that classical physics is valid. You derive it from Hamiltonian dynamics. Then actually you can make an argument saying that suppose that your system within this Hamiltonian frame actually can be reduced to a stochastic process. Then you can show that this result has to remain valid. So the same formula was derived in the Hamiltonian context, but the shape does not depend, I mean, it's this probability. Okay, it has to be valid for the stochastic process if the stochastic process is consistent with the Hamiltonian description. So if it's a physical system that is consistent with a deeper description, it is valid, I'm sure. Of course, you could apply this would be interesting to any process, and you can define always, for instance, we have these conditions of detailed balance. You can, of course, always attribute to a state an energy such that the thing satisfies detailed balance, and it would be an interesting exercise to do that. So I invite people to apply this formalism. I mean, the inequalities are there, they are correct. So this inequality is a mathematical inequality. It receives physical content because we can connect it to these processes of heat exchange, particle exchange, and the reversibility of time. And so that makes it consistent to apply it to other cases as well.
I think you apply to other different things, such as like a biological system or...
Yeah, okay.
Not from the physics, I mean from
yes.
Cathalogistic maps with noise, these kind of things.
So because this is mathematics.
I have a question which Maybe relate to this, that's why I want to bring now. Because you have many ideas here, okay? It's kind of confusing sometimes. But your starting point is a master equation. And then at the end, you mentioned that the same things can be obtained from the Hamiltonian dynamics, some of the results. Additionally, your definition of entropy, they were known that when you use the piece that come from the Hamiltonian dynamics,
exactly.
the follow you the equation.
Thank you for your question. Yes. So, okay, that's very interesting. So, I mean, this is the other very interesting part of the discussion. So here, in the Hamiltonian, in the stochastic description, I avoid one problem. I start with a description which is from the beginning irreversible. Okay, everybody knows that there is an H theorem in stochastic processes, so there is a direction of time. Your probability distribution goes in one direction and in the other. Problem is that at Hamiltonian level, you don't have a direction of time. So things go both ways. So what do we do? I should tell you what is the derivation in a Hamiltonian system. You need to include the existence of a heat bath. This is essential argument. So, and what is a heat bath? A heat bath is, I have my system. If I bring it in contact with the heat bath, it goes to equilibrium and it exchanges entropy with the heat bath in the way that thermodynamics prescribes it for a heat bath. So I have to put this problem, this issue that he says, I have to put at least that issue under the carpet by assuming that I have a heat bath. Now, this is a separate problem. So really deriving irreversible evolutions from dynamical laws, I could say something about it. But okay. So if you accept that there is a heat bath, but you have a system undergoing Hamiltonian dynamics, you can do exactly the same.
But you did some work, right? When you proof of the Broeck's theorem, you consider a trajectory which were Hamiltonian trajectories. I remember.
Yeah, I've done your work. But this is always when you, so in the beginning you have to thermalize a system and you assume you do this with a heat bath. Otherwise you can, or in a sense, the other thing you could say is I assume that I can start in an equilibrium state. Then it's also okay.
You start with the master equation and there you state that the diagonal elements are all negative.
Yes.
So, how do I think about the ground state then?
No, but these are not the diagonal elements of the transition matrix. This is not a density matrix or something like that. So this is transition probability.
Yeah.
So, and you have, of course, you go from M to M prime, you go from one state to a different state. This is a rate, that's a positive quantity.
Yeah.
It's just a question of notation to define the diagonal elements as those that tell you about the probability of staying in the same state. This is just
okay.
probability for not jumping, and this gives you a negative term. That's all. But it's nothing to do with density matrices. So,
so what if you include noise?
So if you start from a master equation, you can go to a Langevin equation. And so, mostly Udo Seff and some other people, Japanese people, they have done most of this. Yeah, I'm sorry. Most of this for Langevin equations. So the reason why, well, it's all okay. It's very nice because people in soft condensed matter can do experiments. They can measure. I think there are like 5 or 6 or 7 PRLs where they check all these concepts for continuous processes in time. Now the reason why I could have talked about it, but there are several reasons why I prefer this as a presentation. Certainly because, of course, stochastic processes have calculus problems, so it's technically not so simple. The discrete case includes, a random walk includes diffusion process, so the discrete case is more general. And the connection with statistical mechanics is much clearer, where you have energy levels and you understand where this work comes from. But they have done exactly the same for continuous processes. It all works. Actually, it started to some extent more in that field than in the discrete version.
What about processes which are normal problem that has some memory on the
I have not worked, people have done this also for, well, the first thing of course is, some Markovian processes can be embedded in Markovian processes by including variables. And my other answer is that in the end, you expect that the non-Markovian process has a Hamiltonian version underneath it. So if I prove it at a Hamiltonian version, And then there is a limit in which this Hamiltonian goes over in whatever stochastic process you have. This theorem has to remain valid because it's valid.
But then it would be a question of time scale. So
yeah, it's just a question of time.
You see as Markovian, and then some time scale you don't
So
see.
here, maybe I should mention the assumption that I do about the probability rates, that they are time dependent. Of course, this time dependence has to be smooth enough so that this detailed balance condition is still valid. But it's a kind of consistency. So if you start to change very rapidly, probably variables you have put under the carpet will also appear. So this is an assumption. But I don't think this is very fundamental. You see, what we try to do now, you know what happens when you have a new theory, like how thermodynamics originally started, is they thought, well, this is something for chemists. And then say, well, maybe some engineers who want to make engines. And then people started to realize, oh, but this has black body radiation. What is the black body radiation? And now we have entropy of black holes. So why are people so, have such great feelings about the second law? Because it has survived all these things, and it has applied to phase transitions and so on. We have to go through the same process, and I cannot promise. Maybe there is a limitation. I personally don't think it, but I can be wrong. So there is one problem is to, this stochastic entropy is minus the log of P, but in a quantum description, P is replaced by a density matrix. So this means that S becomes an operator. I don't know, I just don't know. The people have proven the integral theorems. So some theorems are there, but we are not yet able to copy completely, you know. So it was also the case for quantum, von Neumann also introduced quantum entropy, which is still, the trace of rho of rho. Nobody knows if well, you see. But nevertheless, people believe the second law. And I think this formula is in good stand.
So you started with the assumption, the Markovianity and the discreteness of the level. You told a lot about the Markovianity, what about the discreteness?
Yes, so I mentioned this. So if you can take continuum limit, there is no problem.
There's not something fundamental about the discreteness.
No. So I like it because, in principle we know, or we assume that energy is a discrete space. This is what quantum mechanics tells us. So this is the problem in statistical mechanics. You do statistical, once you do statistical mechanics, you immediately say, oh, this is my system, it has discrete states, and you work with it, although you have a Maxwell-Boltzmann distribution with continuous speed and so on. So, I just think it's nicer to start discrete because we know this is what the fundamental description is about. But and it includes a continuum. Yeah, you can do continuum.
Can you relate this thing of going trajectory and then back with path integrals?
Yeah, so you could, these are really path integrals. So this is probability for paths. But if you divide two probability, it's much simpler. The ratio of the two probabilities, all the volume elements cancel out, so to say. So that's why I just use this. It's a little bit notation. How do you say it's abusive? This notation to say P of probability of a path pi is the probability density in functional space in principle. But so it's
All these things should be demonstrated in principle for any Lagrangian mechanics.
For any
Lagrangian mechanics.
Yeah. So for instance, this was like an exercise that we did, and I think there was a paper on that. One of the examples where we verified the fluctuation theorem is a fusion through a hole. So we calculate how many particles go from one side to the other, and this of course is a fluctuating quantity, and you can calculate entropy production. And then we redid the calculation when we assume that the motion of the particle is relativistic. So that the distribution is no longer Maxwellian, it's the name distribution. We do everything, and it still works. So it's if you also look at the classical derivation, which I didn't give, the Hamiltonian derivation is interesting because it shows you the two ingredients. The two ingredients are the fact that trajectories retrace their steps when you invert the velocities, and the other ingredient is Liouville, which is the fact that density in phase space is conserved. And this is basically in quantum mechanics, this is the unitarity of the time evolution. This is the fact that the laws of physics are invariant under translation in time. That's what you need. That's all.
Any other questions? Yes, Chris will be here 3 more weeks. He has offered himself to give extra talks with some of the details that were left in his talk, so we might, after this, enough interest, prepare one of those.
Yeah, we can just, I don't know how it's organized, but if there is interest for some more where we do the calculations, I am always willing to send an email to